the Crochet Coral Reef project is based on a number of different ideas, but a critical one is that if you look at all of the, if you look at this thing, it looks rather like a piece of coral, and what you have is this sort of frilly crenellated surface, and our eye immediately recognizes this as a sort of marine type organism. It also looks a bit like, some kind of a lettuce. And what these organisms have in common, what a lot of coral reef organisms that have these frilly crenellated surfaces have in common, actually with lettuces also and with some species of cactuses, is that they are all biological manifestations of a kind of geometry called hyperbolic geometry, which is an alternative to the flat or Euclidean geometry that we learn at school. And it turns out that there are three different kinds of geometries. There's the canonical Euclidean geometry. Then there's also the geometry on the surface of a sphere. So just think about a beach ball, just the skin of the sphere, not the interior of it. So we're just talking about the two-dimensional surface. And then it turns out that there's another kind of surface which geometrically is the opposite of a sphere. And this is called a hyperbolic surface. And so one way of thinking about these surfaces is that a Euclidean surface, which is flat, has zero curvature. A sphere, which sort of wraps around on itself, has positive curvature. And just as there are positive and negative numbers, so it turns out there are positive and negative curvature spaces. And this is hyperbolic geometry, is what's called a negative curvature space. And one way of thinking about it is that it's the geometric opposite. It's the geometric equivalent of the negative numbers. So just as there are zero positive numbers and negative numbers, so there's zero positive and negative curvature geometries. And what's interesting about this is that mathematicians spent hundreds of years trying to prove that anything like this was impossible. Even though they knew about spheres, they couldn't conceive that there would be the opposite of a sphere. In fact, they were convinced that nothing like that was possible based on Euclid's laws. And it was only after hundreds of years of trying to convince themselves that it was impossible that in the early 19th century they finally were forced to admit that it was mathematically possible. So they had this idea, they knew symbolically that this thing mathematically existed, which was negative curvature space, and they called it hyperbolic space. But they didn't know what it looked like, and what was astounding is they didn't realize it was embodied in the world around them. And it wasn't until much later that people began to realize, lettuces are negative curvature spaces. So are a lot of kelps and nudibranchs and sea sponges and corals. All of these frilly crenellated forms, they are negative curvature spaces. So even though some of the greatest mathematicians in our society had been trying to prove these things impossible, nature had been doing it for hundreds of millions of years. Nature had been using hyperbolic geometry very widely, and in fact hyperbolic structures exist in many different places in the world, including in structures in our guts and on the surfaces of cells. And there's a very good reason why that is, and it's because these surfaces, it gives you a lot of surface area within a given volume. So if you want any place where you need to maximize nutrient intake, it's good to have maximum surface area. So corals, for instance, are stationary. They're sessile creatures, they're rooted in the sand. They can't go chasing after their lunch, so they basically have to wait for their lunch to waft through the water. So they want to have a maximum surface area to capture the lunch as it walks by, as it floats by. So nature has had a love affair with hyperbolic geometry, but it took mathematicians thousands of years to discover that these surfaces exist. And as I said earlier, even though mathematicians had the ideas of this, and when I was at university I learned this purely symbolically, we didn't have a model for it, and that made it very hard to think about it. You could do the equations, because things like parallel lines behave differently on a hyperbolic surface than they do on flat Euclidean surface. Triangles behave differently. The interior angles of a triangle on a hyperbolic surface don't add up to 180 degrees, add up to something different. It's really hard to imagine how that can be. What happened in 1997 that changed all of that was that a mathematician at Cornell University, Dr. Dinah Taimina, she realized that she could make models of these hyperbolic surfaces with crochet. And so she started making these models to demonstrate the mathematics of hyperbolic geometry. And you can actually stitch theorems onto the surface of these models, and it makes it extremely helpful for students in learning higher mathematics. So at Cornell, she and her husband, Dr. David Henderson, who's a big geometer there, they use her hyperbolic crocheted models to teach non-Euclidean geometry to their students, and it makes it so powerful as a learning tool. It doesn't introduce new mathematics, but it shows you physically what these things look like. And to understand the importance of this, you can think about it this way. Imagine that you lived in a world that was just Euclidean. And then one day some mathematician came along and said, you know what, we've discovered there's this thing called a sphere. You know, it's round and it comes together at the ends, all these ends. And you think, what could a sphere look like? You know, I can understand this thing intellectually, but I can't see it. And then one day some bright person came along and said, look, here's a beach ball. I'm showing you what a sphere looks like. And you go, finally I can see it. Well, that's what Dana did with developing these models of hyperbolic geometry. It's such a powerful thing to be able to hold one in your hand and really see its properties. But as I said, the irony is that although mathematicians couldn't see these things, nature has been doing it since the Silurian age.